Hello students, in this video we'll discuss properties of the Legendre polynomials that come from the generating function. Let's recall we have the following relationship for the Legendre polynomials, that 1 over the square root of 1 minus 2xt plus t squared is the sum, n goes from 0 to infinity, of Pn of x t to the power n, and we can check that this series is valid for x between -1 and 1 and t strictly less than 1 in absolute value, or less or equal to 1 based on that radius of convergence. Okay, and so this is the generating function for the Legendre polynomials. It comes from the same ideas of using generating functions for recursively defined sequences, which you've seen previously. Now what I would like to do is the following. If I take this function over here and square it, I'll have two sums over here. So in other words, what we can conclude from this is 1 over 1 minus 2xt plus t squared is equal to the sum n goes from 0 to infinity. The sum m goes from 1 to infinity, 0 to infinity rather, of Pn of x, and then Pm of x, t to the n plus m, right? So I formally square this, and now I know these functions Pm and Pn, when n is not equal to m, are orthogonal with respect to the Lebesgue measure between -1 and 1. So if I'm going to integrate both sides of this equation with respect to, from -1 to 1, right? So integrating, we have the integral from -1 to 1 of, with respect to t, with respect to x, of course, dx over 1 minus 2xt plus t squared is going to be what? It's going to be just the single sum now. Now when I integrate this from -1 to 1, let's remember what happens over here. So we integrate from -1 to 1, -1 to 1 dx. It turns into a what? These terms over here are going to turn into a delta and m times some constant, right? So in other words, this is going to be a delta and m times the L2 norm on -1 to 1 of Pn squared, like that, okay? That's going to force m to be equal to n. So what I'm going to get over here is I'm going to have, of course, and that's going to be t to the power 2m. So this is going to give us what? This is going to give us the integral from -1 to 1 of Pn. But of course, I have to sum this up, right? We're going to sum n goes from 0 to infinity. So n goes from 0 to infinity. So I'm going to replace all the m's with n's, right? And then we're going to have a what? The L2 norm of Pn to 2, t to the 2n, okay? So now I have an infinite series over here just in terms of the L2 norms. And of course, what are these Pn's? Of course, those norms. So Pn squared is just the integral from -1 to 1 of Pn squared dx, like that, okay? Good. And so now I want to figure out this integral over here to compute these things. So let's do it. So let's recall, let's do the general formula. So here's a lemma. The lemma is that if I integrate from -1 to 1 of just dx over a plus bx, what will this give me? This is going to give me a 1 over b log of a plus bx, like that. And then what will we have from -1 to 1? -1 to 1 will be a 1 over b, and then a what? 1 over b, and then a log of a plus b. Log of a plus b gets a positive sign, and then the log of a minus b gets a negative sign, so I have a plus b over a minus b. Okay, excellent. And so now what's playing the role of our a and b? So for us, playing the role of a is going to be 1 plus t squared, and playing the role of b is going to be a -2t, -2t. That's our formula. So what can we conclude from this? We can conclude that the integral from -1 to 1 of dx over 1 plus t squared minus 2xt is going to be equal to what? Is going to be 1 over b, which is -1 over 2t, so 1 over 2t with a negative sign like that. And then what? And then the log, and of course these are natural logs, right, of a plus b, so that's going to be a 1 minus 2t plus t squared. That's exactly 1 minus t quantity squared. And if I do a minus b, that's going to be a 1 plus 2t t squared. That's a 1 plus t quantity squared. 1 plus t quantity squared, like so. Great. And now what happens is the negative sign is going to flip, and the 1/2 is going to eliminate those squares. So this is just going to be 1 over t, the natural log of 1 plus t over 1 minus t, right? So in other words, what we have over here is we have that this infinite series over here, that is a Taylor series, right, or a Maclaurin series, is the Maclaurin series for this function over here. So if I can find the Maclaurin series for this function, I'll be able to compute these L2 norms of the Legendre polynomials. Great. And so now how do we do that? So let's recall this is like just basic Calc 2. So we recall from Calc 2 that 1 over 1 minus t is the sum. N goes from 0 to infinity of t to the power n, where t is between -1 and 1, and 1 over 1 plus t is this alternating series over here. N goes from 0 to infinity of -1 to the n, and then t to the n. Okay, so those are the Maclaurin expansions for those functions, 1 over 1 minus t. Of course, that you can think of that just like the present value of perpetuity, right? That's how we think of it in terms of financial mathematics. And so now if I integrate these things over here, what will this tell me? This is going to tell me that negative the log of 1 minus t, because of the extra negative sign, is going to be the integral of this expression over here. Is going to be the sum. N goes from 0 to infinity of t to the n plus 1 over n plus 1, like that. Great. And that will tell me that this thing over here, so this is going to give me the regular log of 1 plus t, is going to give me what? Is going to be the sum. N goes from 0 to infinity. -1 to the n, right, that sticks around. T to the n plus 1 over n plus 1. Okay. Okie doke. And so now, let me write this in terms, our function over here is what? Is really 1 over t, and then in parentheses, the log of 1 plus t minus the log of 1 minus t, like that. Okay. And so I can fill in these series over here. So what's this going to give us? This is going to give us a 1 over t, and then what? And then the sum, n goes from 0 to infinity. Well, the log of 1 plus t is going to be a -1 to the n. And then I can just add that to this thing over here. So in other words, I have a -1 to the n over n plus 1 coefficient over here. And then the negative log of 1 plus t is just a positive 1. So this is going to be a -1 to the power n plus 1. And then what? And then a t to the n plus 1 over n plus 1. Like that. Excellent. And so now what? And so now that factor of t is going to eliminate this factor of 1, like that. Like that. Those will cancel out. And now when n is odd, this is 0. And when n is even, this is going to give me a factor of 2, right? And so this is really just nothing more than the sum. N goes from 0 to infinity. There's only, n can only be even, so I can replace n with 2n. So this becomes a 2 over 2n plus 1. T to the 2n. So in other words, this function over here, 1 over t log of 1 plus t over 1 minus t, has this Maclaurin expansion, right? And so now, here's the Maclaurin expansion for that function, and here's the Maclaurin expansion for that function. So from this, what can we conclude? We can conclude from this that the integral from -1 to 1 of Pn squared of x, if I take the nth Legendre polynomial, square it, dx, what are those numbers over there? Those numbers are exactly 2 over 2n plus 1, and therefore we have, when n is of course what? So those are the short, of course, the even moments of the Legendre polynomial, but this gives all the L2 norms of the Legendre polynomials. And so now when we're going to write down the formal Legendre Fourier expansions of a function between -1 and 1, we're going to have to normalize all these functions by this number over here, 2 over n plus 2 over 2n plus 1, and that will be embedded in our Fourier-Legendre coefficients when we do Fourier-Legendre expansions. Thank you very much.